In this section, we're going to discuss oxidation states. First, what is oxidation and what is reduction? They work together in what are called redox reactions, which involve the transfer of electrons from one species to another. The substance that gains electrons is said to be reduced, while the substance that loses electrons is said to be oxidized. So let's look at this example that we have here. We have this copper solid that becomes copper +1. So what happens there? We have no charge on the solid, and we have a +1 charge on the aqueous ion. So what's happening there is we're losing an electron to become positively charged. Opposite of that, let's look what happens here with this silver. We start with a silver ion and then end with a silver solid with no charge. What's happening here is the silver is gaining the electron. Where is it gaining it from? From the copper solid that's losing the electron. So those two things happen together. So in this reaction, the copper atom is losing an electron to the silver ion, which gains that electron. So copper is oxidized, silver is reduced. All right, let's use this table to summarize what oxidation is and what reduction is. In oxidation, the substance loses electrons. We have the first part of this mnemonic device, LEO here. Losing electrons is oxidation. When you lose electrons, the oxidation state increases. So if we look at this example down here with the sodium, we go from an oxidation state of 0, which we're going to talk about in just a second, to an oxidation state of +1. So that's an increase. Okay, and electrons are a product because they're being lost. So this sodium loses electrons or undergoes oxidation to form the sodium ion and a free electron. Okay, the free electron participates in the reduction part of the reaction. Okay, so reduction is a gain of electrons. The other part of this mnemonic device is GR. Gain of electrons is reduction. In this case, the oxidation state decreases. So in this reaction down here, magnesium 2+ has an oxidation state of 2+. After gaining 2 electrons, has an oxidation state of 0. So it goes from 2+ to 0. That's a decrease in the oxidation state. And as you can see here, electrons are a reactant because they're being gained in the formation of the product. We can remember this by the following expression. Leo the lion says GR. Losing electrons is oxidation, gaining electrons is reduction. So we've sort of been alluding to it, but let's discuss now how we determine oxidation states. In order to determine if a reaction is an oxidation-reduction reaction and which element is oxidized and which is reduced, we have to track the oxidation states of elements throughout the reaction. Let's take a look at this example here. We have zinc plus 2 hydrogen ions produces a zinc 2+ ion plus hydrogen H2 in its elemental form. In this case, the zinc metal starts with an oxidation state of 0 and ends with an oxidation state of +2, the charge of that ion, right? Whereas for the hydrogen, it goes from +1, the charge of the ion, to 0. We're going to talk in the next slide about why it's 0. We can see that both the zinc and the hydrogen charges change, or the oxidation states change. So this is definitely a redox reaction where the zinc is losing electrons and the hydrogen is gaining electrons. All right, there are 7 rules for determining oxidation states. And if those rules are ever in conflict, the rule that is higher in the list has priority. We'll explain each rule in sequence so they make sense, and that way it will minimize the amount of memorization that needs to be done. All right, here's rule number 1 for determining oxidation states. All elements in their standard or neutral state have an oxidation state of 0. If the element has a charge listed, this is its oxidation state. So, hydrogen gas, H2 gas, is this element in its standard state. So it has an oxidation state of 0. That's also true for metals like calcium. In its solid state, oxidation state of 0. But these two ions, sodium plus ion, fluorine minus ion, their oxidation state is equal to their charge. Anytime you see an individual element or ion, that is the rule you will use for determining the oxidation state. Here's rule number 2 for determining oxidation states. The sum of the oxidation states of the elements of a neutral molecule must equal 0, and the sum of the oxidation states of a polyatomic ion must equal the charge of that polyatomic ion. So as an example, if we had a neutral molecule, something like carbon dioxide, the sum of oxygen's oxidation state and carbon's oxidation state has to add up to 0. We're going to talk about the oxidation states for each of these individual elements in the compound in a few more slides here in a different rule. But the purpose of this rule is to know that the overall charge of the carbon oxidation combined with the oxygen oxidation has to add up to 0. The same thing is true for like a ionic compound like sodium chloride. Those two oxidation states have to add up to 0. And then for a polyatomic ion, like say phosphate, PO4, 3-, the sum of the oxidation state for phosphorus plus those 4 oxygens has to add up to a -3. So again, there are some more details coming and a few more rules here on how we start assigning oxidation numbers, but we have to know that the overall sum has to add up to either the charge of the ion or neutral if it's a neutral molecule. Rule number 3 for determining oxidation states. In compounds, group 1 and group 2 metals have oxidation states equal to their normal ionic charge. Group 1 metals have an oxidation state of +1, and group 2 metals have an oxidation state of +2. So, as an example, this sodium has an oxidation state of +1 in this compound, and this magnesium has an oxidation state of +2. Rule number 4 for determining oxidation states. In compounds, fluorine has an oxidation state of -1. This is the same as its normal ionic charge, so it's just like the prior rule for metals. So if I did sodium fluoride, we said that group 1 metals were +1 and fluorine was -1. Of course, if you add those two together, that satisfies rule number 2, which says that the overall sum of the oxidation states has to add up to the overall charge of the molecule, which in this case is neutral or 0. Fluorine is listed separately from a later rule that we're going to see, rule number 7, for group 15, 16, and 17 elements, because fluoride's oxidation state has a higher priority than those indicated by the other rules. So fluorine is always going to have an oxidation state of -1. Rule number 5 for determining oxidation states. Hydrogen has an oxidation state of +1, except when bound to metals from groups 1 or 2. When bound to those metals will have either an oxidation state of +1 or +2. Hydrogen will have an oxidation state of -1. So here's an example of that. If I have sodium and hydrogen, we saw back in an earlier rule that those group 1 and 2 metals are always +1 or +2, which means in this case hydrogen has to be -1 because the overall oxidation states has to add to 0. Okay? If hydrogen is not bonded to a group 1 or a group 2 metal, so as an example H2O, then it has an oxidation state. So the oxidation state here is +1 for each of those 2 hydrogens. Maybe you can think ahead. What do you think the oxidation state for this oxygen will have to be in order for the overall oxidation states to add to 0, which is the neutral water molecule? All right, here is rule number 6 for determining oxidation states. Oxygen has an oxidation state of -2, its normal ionic charge, except when in a compound and bound to another oxygen. When oxygen atoms are bound together in a compound, they are called peroxides. In peroxides, oxygen has an oxidation state of -1. So let me give you a couple of examples. In the previous slide, in the previous rule we were discussing water. In this case, we know that hydrogen has an oxidation state of +1. Now this subscript 2 means there's 2 of them. So we have an overall +2 being contributed by those hydrogens. In order for the molecule to be overall neutral, then this oxygen, as we see here, is -2. Okay, now, except when bound in a compound and bound to another oxygen. So in a compound where we have oxygens bonded to other oxygens. So here's an example of hydrogen peroxide. Okay, so that's peroxides that we're discussing here. In this case, the prior rule has precedence. So hydrogen is +1, and there are 2 of them, which gives us an overall +2. Now we have 2 oxygens, but we have to be overall neutral, which means that each of these oxygens is -1, and there are 2 of them, so that we get an overall neutral charge. Rule number 7, in binary compounds with metals, elements in group 15, 16, and 17 have oxidation states equal to their normal ionic charge. Group 15 elements have an oxidation state of -3, 16 -2, and 17 -1. So if I was going to look at something like sodium phosphide, remember from our previous rule, group 1 metals are +1, and there are 3 of them, which means that in order for this to be overall neutral, this phosphorus has to be -3, which is the same as its ionic charge. And that would be true if this was oxygen or if it were chlorine. So group 15, 16, and 17. All right, here's a summary of the rules for determining oxidation states. 1, any pure element has an oxidation state of 0. 2, the sum of the oxidation states of the atoms forming a molecule or ion is the net charge of that molecule or ion. 3, in their compounds, group 1 metals have an oxidation state of +1, and group 2 metals have an oxidation state of +2. In its compounds, fluorine always has an oxidation state of -1. 5, in their compounds, hydrogen atoms have an oxidation state of +1, except when combined with group 1 or group 2 metals. In that case, they have an oxidation state of -1. 6, in its compounds, oxygen atoms have an oxidation state of -2, except in its compounds in which oxygen is bonded to oxygen. Those are called peroxides, and in that case, the oxidation state is -1. In binary compounds with metals, group 17 elements have an oxidation state of -1, group 16 elements have an oxidation state of -2, and group 15 elements have an oxidation state of -3. All right, let's take a look at an example of a redox reaction. Let's ask the question, which species in this reaction is oxidized or reduced? In order to figure that out, we have to determine the oxidation states for each element. Okay, so let's go through the rules. Remember that elements in their standard state have oxidation states of 0. So this aluminum here has an oxidation state of 0. It's just aluminum. There's no charge there. It's just aluminum metal. The same thing is true here of this O2. That's the way we find oxygen in its natural diatomic state, right? It's O2, the element, the gas. Now, we're producing Al2O3, all right? And so that's an ionic compound, right? That's an ionic compound. So we're going to start with the oxygen. So aluminum is a group 13 metal. We don't have any specific rules about that, but we do know that oxygen, when it's in a compound, has an oxidation state of -2. So this oxygen is -2. Now there are 3 of those, okay, which gives us an overall -6 oxidation contributed by the oxygens. Now what about the aluminum? Oh, I used the wrong color. I'm going to fix that so it's not confusing. So -2 times 3 gives us an overall -6. Now, this compound overall is a neutral, right? Al2O3 has no overall charge. So that means I need to contribute an overall +6 from the aluminum. Now I have 2 atoms. What would the oxidation have to be in order for 2 atoms to contribute +6? So it would have to be +3. So the aluminum goes from 0 to +3, and the oxygen goes from 0 to -2. We're going to show the answer on the next slide, but before I do, can you decide which one of these is oxidized and which is reduced? Which one loses electrons and which gains electrons? All right, so this slide summarizes exactly what we just discussed. Aluminum and oxygen both start at 0. Aluminum ends with a +3 oxidation, oxygen with a -2. So again, which element lost electrons or was oxidized, and which gained electrons or was reduced? Now, what's oxidized and what's reduced has to be a reactant. So it's either aluminum or O2. Okay, which one loses electrons? So going from 0 to +3, which we see here from 0 to +3, that's losing electrons, right? Because we're getting more positive, we're losing negatives, we're getting more positive. And going from 0 to -2, we're gaining negatives, we're gaining electrons, right? So let's look here at the next slide and summarize that. Going from 0 to +3, each aluminum loses electrons, so that's the oxidation reaction in blue. And the reduction is gaining electrons, so going from 0 to -2, each oxygen is gaining electrons, so that would be reduction.